Alright, welcome back everybody. In this video we're going to look at the slope of polar curves lesson and the slope formula for polar curves, and also how we can use this to find slopes of polar curves. Before I get too far along here, please note there's a big old typo in this slope formula. It's missing a sine of theta in the numerator. But to find the slope of a polar curve, dy dx, for a particular polar point r theta, all we have is dy d theta over dx d theta. dy d theta is sine of theta f prime of theta plus f of theta cosine of theta, and dx d theta is f prime of theta cosine of theta minus f of theta sine of theta. And so we can use this formula. I say below, well, this is a very nice formula to represent the slope of the curve. I personally have never used it once. I'm going to show you where this formula comes from, and that's what I tend to do here. If you want to memorize this formula and use it, you're more than welcome to. I can see that it has some utility. I'm just stubborn and set in my ways a little bit, and don't feel like memorizing this formula. So the whole idea here is we have this function, r equals f of theta, and because of the way that our Cartesian coordinates behave with respect to the polars, we know that x is equal to r cosine of theta. So x is equal to f of theta cosine of theta, and y is equal to f of theta sine of theta. Now if we take the derivative of these with respect to theta, dx d theta, using the product rule, is just going to be f of theta times the derivative of the cosine, which is negative sine of theta, plus cosine of theta times the derivative of f of theta, which is f prime of theta times cosine of theta. That's dx d theta. And dy d theta is f of theta times the derivative of the sine, which is cosine, plus the sine times the derivative of f, which is f prime of theta, sine of theta. And so you can see from this that since dy dx is equal to dy d theta over dx d theta, my slope is f of theta cosine of theta plus f prime of theta sine of theta all over f prime of theta cosine of theta minus f of theta sine of theta. Like I said, if you want to memorize that formula and use it, feel free to. I just basically every time start with my x and my y based off of my curve r equals f of theta and find dy dx accordingly. Alright? Alright. Let's go on and look at example 1. Special tangents to a polar curve. Specifically, we're talking about horizontal and vertical tangents here. We have a horizontal tangent to a curve anytime where dy d theta equals 0, but dx d theta does not. And we have a vertical tangent to a curve wherever dx d theta equals 0, but dy d theta does not. So if we're looking for horizontal and vertical tangents, we're going to look for where dx d theta and dy d theta are 0, and then utilize this information right here to figure out if they are vertical tangents or horizontal tangents. If we have points where both of them are 0, we need to investigate the curve more to decide if there's a vertical or horizontal tangent at the point. Alright, so to get myself started here, x is equal to r cosine of theta. So x is equal to 1 minus sine of theta times the cosine of theta, since our function r is 1 minus sine of theta. And y is equal to r sine of theta. And I'm supposed to find all the horizontal and vertical tangents to the curve for theta values between 0 and 2 pi. Alright, so I find dx d theta. That's 1 minus sine of theta times the derivative of cosine, which is negative sine, plus cosine times the derivative of 1 minus sine of theta, which is negative cosine. And so dx d theta is equal to negative sine of theta plus sine squared of theta minus cosine squared of theta. And dy d theta is going to be the quantity 1 minus sine of theta times the derivative of sine, which is cosine, plus sine times the derivative of 1 minus sine, which is negative cosine. And so this is equal to cosine of theta minus 2 sine of theta cosine of theta. And now I need to find all the values of theta where these are equal to 0. So I'm going to go ahead and do that. I'm going to solve these equations. I'm going to use my calculator to help me. We're only concerned about theta values that are between 0 and 2 pi. So I'll start with the first one. We've got negative sine of theta plus sine of theta quantity squared minus cosine of theta quantity squared. And I'm going to graph this in a window between 0 and 2 pi, since that's what I'm concerned with. And I'll use a scale of, let's use pi over 4. And I don't really need to see a whole lot of the y values, I just need to see where they cross the axis. So we'll go ahead and graph this. And we see a couple places where this is going to be equal to 0. They're not always readily identifiable, so let's see, we've got a 0. Looks like we've got a 0 here. And that should be at pi over 2. I don't know if this will find that 0 for me, or if it'll give me a no sign change error, since it goes from negative to 0 to negative. Come on, you can do it. No sign change. So that happens at theta equals pi over 2. Let's see where else we've got here. Ooh, sorry about that. We've got a 0 at .665, which, if you don't recognize it, that's about 7 pi over, in fact, that is 7 pi over 6. And we've got a 0 at come on, let's go. .759, which is 11 pi over 6. If you don't know how I'm getting those values, you should talk to me about that sometime. I can show you. But I don't have time to do it right now. Alright, and find the zeros of this one. there are a few of them. Wish I could move my cursor faster on here. I feel like I'm spending all of my time cursoring. At 0.524, which is theta equals pi over 6. And pi over 2. And .617, which should be 5 pi over 6. And I fear I'm going to run out of time here. And 4.712, which is 3 pi over 2. Okay, so looking at these, we have 7 pi over 6 and 11 pi over 6 are both going to be places where there are vertical tangents. Pi over 6, 5 pi over 6, 3 pi over 2 are all going to be places where there are horizontal tangents, and pi over 2 is somewhere where we need to investigate more what's going on. Okay, so now how do I find these horizontal and vertical tangents? Well, I substitute theta, these theta values that we found, back into these original equations for x and y. Alright, so if I put 7 pi over 6 in here, the sine of 7 pi over 6 is a half, so that's a half, times the cosine of 7 pi over 6. Oh gosh. Let me try that again. The sine of 7 pi over 6 is negative 1/2. So that's going to be 3 halves. And the cosine of 7 pi over 6 is negative square root of 3 over 2. So 3 halves times negative square root of 3 over 2. That's going to be at x equals negative 3 root 3 over 4. We should have a we should have a horizontal tangent. I'm sorry, we should have a vertical tangent. And at 11 pi over 6, if I put 11 pi over 6 and go back in there, I'm going to get x equals, my goodness, that's again 3, that's going to be positive. It's 3 root 3 over 4. And for all of these, I'm going to put those back in there. Pi over 6, let's see, that's 1/2 times 1/2. So we've got y equals 1/4 for that equation. For 5 pi over 6, we've got the same vertical line. For 3 pi over 2, the sine is negative 1. So we get y equals negative 2. So those are horizontal and vertical tangents. With this one, the pi over 2, I need to figure out what dy dx is, and it's going to be 0 over 0 at that point, and so I would have to use L'Hopital's rule to figure out if that's going to be a horizontal tangent or a vertical tangent, and in fact it works out that it is a horizontal tangent. Don't have time to do L'Hopital now, but it works out that it's a horizontal tangent. And so at pi over 2, I put that back into y, and I get the horizontal tangent, y equals 0. Alright, that's all I have time for today. See you guys next time. Have a great rest of your day.